Swayam Prabha. Digital India. Educated India.
So we had talked about the various classifications of phase transition. We had talked about first order transition. We have talked about second order transition. We have talked about the lambda transition. Now we are going to look into, before we look into mixtures again, we have done only a simple mixture. We have of pure substances. In forthcoming classes, we are going to look into mixtures of solid and liquid, or liquid-liquid. Let us see and look into the colligative properties. So before that, we have to introduce the non-ideality. Why do we need to introduce non-ideality? Whenever we are talking about the ideal system, we have developed a set of equations, thermodynamic equations based on ideal gas law. Okay, we have taken the most important thermodynamic property, for example, the Gibbs energy for an ideal gas, how the Gibbs energy changes with pressure. Suppose this is the equation which we have taken. What we would like to introduce here is, if I have some non-ideality introduced, then the equations which we have developed so far, will they change all of a sudden, or will we be able to retain the equation and use them with some modification, so that the whatever we have applied, whatever we are going to face in reality is going to be complex, but can we still retain the ideal equations and go forward? That is what the entire introduction of this non-identity discussion is about. So what we are looking into, we are first taking a very most relevant property, thermodynamic property, the Gibbs energy. Gibbs energy variation with pressure we have already seen for an ideal gas. What is that? What does that tell us? The Gibbs energy for a given pressure at the pressure we want to find out is going to be the Gibbs energy at standard state plus nRT ln P by P naught. P naught is the standard pressure which is defined at 1 atmosphere. Sometimes we do not write the P naught, but you have to remember that P naught is always existing. So if I want to find out the per mole, then I can write down in terms of the chemical potential. So chemical potential at any pressure P, which we need to find out, is equal to, will be again given by the G naught per mole, that is the standard chemical potential, plus RT ln P by P naught, where P naught is 1 bar. Now the simplest modification which we have come up for replacing this equation for an ideal gas to that of a real gas is, instead of P, I introduce a new function known as the fugacity, and we define that as F. Okay, so instead of writing P by P naught, I now replace the equation which I had for the pressure variation of G with a term F in place of the P at which we are doing the measurement. Okay, so I modify the equation accordingly and say that the Gibbs energy at that particular pressure is nothing but the standard Gibbs free energy plus RT nRT ln F by P naught. So the chemical potential will be given by mu at that particular pressure equal to the standard chemical potential RT ln F by P naught. This F by P is known as the fugacity coefficient. So if I want to find out the fugacity, it is nothing but the fugacity coefficient into the pressure. And when will the gas start behaving, a non-ideal gas start behaving ideally? It is going to happen only when the temperature is very high or the pressure is very low, right? So if I have the conditions of limit of pressure approaching 0, then what happens to this ratio? This ratio becomes 1. So that means the fugacity coefficient becomes 1. So under the limit of pressure approaching zero, that means the system is approaching ideal condition. The the fugacity should be equal to 1. You have seen this same thing when we are dealing with solution. In solution, we write activity. Say a chemical potential of a species I is nothing but the chemical potential of that I species in the standard state part plus RTLN activity which we write for that particular species, which we write AI. What is AI? Activity is nothing but the activity coefficient into the concentration of that particular species at, say, we define this for that species at ith species at that particular concentration. We can write down in terms of the activity. And for this, what do we have? What is the limit we have? When at very dilute conditions, when the concentration of these I species is very, very low, then it behaves like an ideal solution. So under the condition of very, very low concentration, the activity coefficient becomes equal to 1. That time activity is equal to concentration. That means what under the limit of the concentration of the species approaching 0, A by C, which is the defined as activity coefficient, is equal to 1, which implies the under the limit of C approaches infinity, the activity coefficient becomes equal to 1. So when we write this general expression, when the activity coefficient is becoming 1, then the activity of that particular species is equal to the concentration of that species at that given temperature and pressure conditions. This we have already seen in various examples when we are dealing with reactions equilibrium. We are talking about, when we are talking about a solution, we don't take the concentrations in terms of moles per liter, but we take the concentration in terms of the molality. Okay, we take the concentration in terms of molality, and the activity is defined as the activity of that particular species divided by C naught equal to gamma, where the C naught is defined as 1 molal, 1 kg of the substance in 1 liter of the solvent. That is 1 molal. So when we talk about solutions, we talk about activity, and when we talk about gases, we talk about fugacity. In solution, we have activity coefficient becoming equal to 1 at very dilute conditions where concentration approaches 0. And in gases, the fugacity becomes equal to the pressure when the activity coefficient, fugacity coefficient is approaching 1 under limits of pressure tending to 0. That means at very, very low pressure. That time, the gas starts behaving like the idealized system we have taken so far. Okay, so this is a new defined expression for a gas which is not ideal. If it is not ideal, then the G can be replaced by G naught plus nRT ln F by P naught, and the chemical potential accordingly will be the standard chemical potential plus RT ln F by P naught. F is the fugacity function. Now, what we have, the fugacity has the same conditions of units of pressure. It is taken, the pressure units are the same as the units for pressure, whatever we take for fugacity. And when pressure approaches 0, the gas approaches ideality, and fugacity becomes tending to equal to the pressure of the gas. It's the measure of the molar Gibbs free energy of a real gas. So a real gas behaves like an ideal gas under the limit of low pressure and high temperature, and they deviate at high pressure and low temperature. This we all know. Now, the measure of the deviation, if you remember, from your previous class in class 11 and 12, you had a factor called as the compressibility factor. This gives you the measure of the deviation from a real to the ideal and the real. And this measure is nothing but the compressibility factor Z. What is that? It is defined as the molar volume of the real divided by the molar volume of the ideal gas. Okay. So what we write down, we apply the ideal gas law and we replace V by equal to RT by P. So I replace RT by P. So P by RT into the molar volume of the real gas is what we have. So if I want to look into the volume of the molar volume of the real gas, it is going to be nothing but Z RT by P. From this equation, from the equation which we have here, fugacity of a real gas can be calculated at a given temperature and pressure if we know the limits. Now, if I want to find out what is the difference between the fugacity of a real gas and the, what do I mean by that, and what that translates into our general expectation of G when we are, or mu, when whatever we are calling it, for a system. Let us look at that. What is that defined as? What you have for a G, a change in G from, say, with at a given pressure and given temperature for any gas can be written like this. This is how we have the pressure variation of G. The pressure G at final pressure equal to G at initial pressure plus the integral of volume and dP. This equation, I hope you remember. How did we get this? How did we get this? This is coming from the fundamental equation where we are taking the variation of G with pressure giving temperature as a constant. G is now defined as delta G is nothing but equal to minus S dt plus
VDP minus SDT.
yes, yes, right,
VDP minus SDT.
yes, minus so VDP minus SDT. So if I take temperature constants, the S contribution is going to be overlooked, and we have the change in delta G will be equal to only the with pressure will be equal to the molar volume, if you remember. So if I expand that equation, if I want to find out what is the delta G, it will be the delta G at the final state equal to the delta G at the initial state of pressure and the VDP integrated over temperature and pressure initial to the final pressure. Do you remember that equation? This we have done how the pressure variation of G is. So this is how you evaluate. Now, what happens if I want to translate that in terms of the mu? I'm talking about per mole. So this becomes the chemical potential of the final equal to chemical potential of initial into the molar volume into the dP integrated over from initial pressure to final pressure, right? So if I can take that difference, what do I write? If I want to take that difference, I say the pressure is from P to P prime, then what I can write? Initial pressure being the P prime and another pressure being final pressure at which we are measuring, if it is that is P, then what do we write? We write this for an ideal gas, right? Can we write or not? Please remember that this is what the definition is. How do we define the mu? I've instead of taking the standard condition, I have applied to the measurement of V at two different pressures. One is P and another is P prime. P prime is the initial one and P is the final pressure at which we are measuring. Okay, so if that is the expression, then what do I get? The integral of the pressure from P initial P prime to P will be nothing but the integration of that the molar volume into dP, and that will be giving me the change in the chemical potential I observed in the from initial to the final. This is the initial to the final, right? And from the expression of G, we can write down, this is the expression of mu and G. G would have been Gp at G naught plus nRT ln P by P naught, right? Right?
Yes, ma'am.
Okay. So what I have here for the ideal gas for this sort of a system, how do I write? I can write this as the integral of V, the molar volume into dP equal to RT ln P by P prime. This is the initial pressure to the final pressure. That is the change in chemical potential I have for this particular case. This change in chemical potential will be equal to nothing but RT ln P by P minus P prime. This is the initial pressure, this is the final pressure. This is how I get it from the difference in chemical potential at the two pressures. And that will be equal to the change in the volume, integral of the volume from initial pressure to the final pressure into dP. This is coming from fundamental equation. And this I have substituted from the knowledge of what is the definition of chemical potential. The standard state of the two will get cancelled off, right? Right? How can we write this? This would have been mu plus mu naught RT. What will this be? RT P by P naught. And this would have been mu naught plus RT P prime by P naught. Right? I have expanded these two and written down this. Am I okay?
Yes, ma'am.
Okay. So you just remember that in this I have plugged in this value of mu. This value of this is for this case, and for the P prime case, this would have been P prime and this would have been P prime. Okay. So if I take this subtraction of these two, then I'm left with RT ln P by P prime minus RT ln P prime by P naught. Right? This will correspond to RT ln P by P naught minus RT ln P prime by P naught. And if I rewrite, I can write that down as RT ln P by P prime, right? Mu naughts will get cancelled.
Yes, ma'am.
Okay. Now suppose F is the fugacity of the gas when the pressure is P, and F prime is the fugacity of the gas when the pressure is P prime. Then I rewrite this expression. Now I rewrite. What will be the change in the integral of the molar volume into dP from P1 to P prime, P prime to P? It will be nothing but this expression which I had written. Instead of this, I will write F by P naught. This is what I have written. Minus the standard chemical potential RT ln F prime by P naught. Right? So for the real gas, I can write down the integral of the V molar volume into dP from p prime to p will be, if it is, if f is the fugacity for the pressure p and f prime is the fugacity corresponding to the pressure p prime, then what do I get? I get RTLN f by f prime, right? Similar to this, similar to this.
Yes, ma'am.
Okay. Now, if I now want to see what is the difference between the molar volume of a real gas and a molar volume of the ideal gas, then I take the difference of the two volumes. One is real, one is ideal, and over the same range of temperature, pressure. At a given temperature, over same range of pressure, P prime to P. Then what do I write? From this, for real, I got this one, right? For the ideal, what I get? This one. For the same change from P prime to P, right? So if I rewrite that, substitute that for the volumes for real and the ideal, what do I get? I get something like this. Yes. Can I write or not? Can I write this? And I rearrange so that I have f by p and p prime by f prime. That will be nothing but the RT taken this side, it will be the integral of P prime to P, the difference in the volumes, molar volumes of the two gases, one is real and one is ideal. Now,
Yes, ma'am.
now when we say that P approaches the P prime, the initial pressure approaches P's a value of 0, the gas starts behaving ideally. And what happens then? Then the P prime, F prime becomes equal to F P prime. When the gas starts behaving ideally, then the fugacity becomes equal to the pressure, right? So if I say the prime P is approaching 0, the initial pressure is approaching 0, then the fugacity associated with that, that is the F prime, will be equal to the pressure associated with that, that is F P prime, right? So the
Yes, ma'am.
same thing we can write the ratio of the P F prime to P prime under the limit condition of P equal to is approaching P prime is approaching 0. This becomes equal to 1. So this part becomes 1, right? As
Yes.
P prime is approaching 0. Now setting this in equation 3. Which is the equation 3 which we have? This is the equation 3 we have. Setting that is in equation 3. What I have, this becomes 1. What do I write now? That means I can write ln f pi p equal to the ln phi 1 by RT 0 to P. Can we write or not? What are we putting in the left hand side and right hand side? Left hand side, we are changing the limit from P prime being equal to 0. And this side, we have taken the P prime by P prime, F prime by P prime equal to 1. Right? So under the limiting condition, what do I have? Under the limiting condition, what do I have? Sorry, what do I have? Under the limiting condition, I have approaching the P1 to be approaching to 0. And if P1 is approaching to 0, then this F becomes equal to P prime. This F prime becomes equal to the, P prime. So this becomes equal to 1. So I rewrite ln phi by P. This is becoming 1. And this limit will change from 0 to P because I have put that P prime is approaching 0. So initial pressure I am changing from P-prime approaching being P-prime to approaching P-prime approaching 0. So if P-prime is approaching 0, I put 0 here, and as P-prime is in the is approaching 0, that means it is going towards behavior of ideal. So the ratio of the f by p will be equal to 1, or p by f will be equal to 1. So this I can set as 1. This limit I can change from 0 to p, right? In this expression.
Yes, ma'am.
All of you with me? The boys are with me? Giridhar, you are with me? Please respond. Are you understanding what I am saying?
Yes,
I'm trying to see the difference in the molar volumes of the ideal gas and the real gas. Real gas minus ideal gas, what is the value I'm getting? I want to see that. And I've set that when the fugacity is F, I say the pressure is P. And when the fugacity is P F prime, I say let the initial pressure be P prime. Okay. So and accordingly, I found out what will be the difference between P real minus P ideal. And P real I have substituted for a change in fugacity from F to F prime to F, and for ideal I have changed the pressure from P prime to P. So this is what I get. And from this I rearrange and I get P by P prime to by P F prime, and I say this F pi P prime or P pi by P prime becomes equal to 1 as the pressure P1, initial pressure P prime, is approaching 0. As this is approaching 0, this becomes equal to this. So this ratio becomes 1. And if I'm putting that limits, I should introduce that limit here also. Instead of P prime, I should write 0 to P, right? So accordingly, we get the equation F by ln F by P, where P prime by F prime it becomes equal to 1, is equal to RT, 1 by RT from 0 to P into the difference in the molar volume dP. And what is phi by P is defined as the fugacity coefficient. So I can write ln phi, right?
Yes, ma'am.
So if you have understood this, now I introduce another manipulation. Is ideal gas Vm is equal to RT by P, and the real gas is Vm is nothing if I in terms of the compressibility factor RT by P into Z. Now substitute Vm in equation 4. Which is the equation 4? This is the one I have derived. Substitute these values of Vm in the equation here. What do I have? For Vm real, this is the value RT Z by P, and for V ideal, it is RT by P. RT you can take common, right? And if I take RT common, the denominator RT and this RT will cancel. Then what do I have? This will be, if this will have only Z, right? Yes, come up and say. This will be, from here I get only Z or Z by P. Yes. How boring it is to just keep telling you what to do. I have taken the Vm defined as Vm RT by P and Vm real as RT Z by P. Z is the measure of the deviation, the compressibility factor. So RTZ, by P, if I put here, this is going to be RTZ by P, and this is going to be RT by P. I take RT common. I take RT common. Then what do I get? This is Z, this is 1 by P, right? All of you getting what I'm doing?
Yes, ma'am.
Yes, ma'am.
Into dP. So now I have an expression. This is the expression I've got. Ln phi integration from 0 to P Z minus 1 by P dP. And this is going to give us how the Z is going to vary with pressure and how this is going to give us a value or expression of the fugacity coefficient. And once we know the fugacity coefficient, we can find out what the fugacity is. If I know, multiply that by the pressure, I can get it. Because phi, if I know, phi into pressure will give me the fugacity. So I can find out what the fugacity is. What so far we have derived? We have derived the expression for finding out the uh, fugacity coefficient in terms of the compressibility factor. And compressibility, why compressibility factor? Compressibility factor because that is the measure of the difference between the ideal and the real from the ideal. And what is that is what we have done. We have taken the molar volume of the real gas minus the molar volume of the ideal gas. Substitute the Vm values for an ideal gas and the real gas. If I take RT common, then I have nothing but here from here I have Z, and from here I have 1. So Z minus 1 by P dP is going to be from the limits 0 to P is going to be the measure of the Ln fugacity coefficient. Right? And if I know the fugacity coefficient and I multiply with the pressure, I get the fugacity. Now, what does this indicate? If you look at the graph, if you look at the graph of molar G with pressure, this is the typical graph we see for a molar G with pressure. Few things you need to notice. As you see the pressure is lowered, this is the condition where this is for the perfect gas, and the purple line, if you can see the makeout, purple line is for the real gas. Perfect gas, when the pressure is the standard pressure of 1 bar, the value corresponding to that is known as the standard molar Gibbs free energy. Okay, and the deviation of this starts as soon as we have a real gas. So what we do? We look at the two plots. Up to moderate pressure, what you see? Up to moderate pressure, what do we have? The perfect gas is higher. The molar value of the Gibbs free energy for a perfect gas is higher up to moderate pressure. And only at very high pressures does the real gas GM become higher than that of the ideal gas. Within the moderate pressure range, what you have? The perfect gas has a higher Gibbs free energy than the real gas. Only at very high temperatures do we have the real gas having higher G Gibbs molar free energy or the chemical potential higher than that of the ideal. Please note, this is something we need to know. Can the GM value or the chemical potential value have a negative value? Yes, it can get negative value when the pressure is approaching very low. So when the pressure is approaching very low, then the GM of the system may have a negative infinity value. How is that? You see this expression? You see this expression and see what is going to happen when you are having, say, pressure approaching zero. When this expression is for fugacity, and if you replace this by P by P naught, then it becomes for the real gas, ideal gas. What will that become? If this is approaching zero, if this pressure is approaching zero, then what is going to happen? This will become a negative infinity.
Yes, ma'am.
This will become a negative infinity. So we do have a negative infinity of GM possible, and that is only possible when the pressures are very low, when the pressure is approaching zero. Okay. Now let us analyze what is happening. What is analyzed? Why is that the GM of the real gases are becoming higher than that of the ideal gases when we go for very high temperatures? Look at the conditions. We have the expression for ln phi, we have the expression for z, and we have the expression for the integral, which we have found out the difference from the difference in the molar volume of the gas in the ideal and the real gas. From there, we have found out what is going to be ln phi from just now the expression which we have derived. Now let us see what happens when the z is less than 1 or greater than 1. See, up to moderate pressure, the 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 deviation or compressibility factor is less than 1. If this is less than 1, z is less than 1, then what does that imply? That means the integral will be less than 1. And if the integral is less than 1, what will be phi? Phi will be also less than 1. Under this condition, what you have, the pressure is higher than the fugacity value for that gas and that given temperature and pressure. So if I have a condition where the pressure of the gas is greater than the fugacity of the gas associated with the real gas, and pressure is the ideal gas, if the pressure of the ideal gas is greater than the fugacity of the gas which is real, what do we say? We say the molecules tend to stick together. The attractive intermolecular forces are dominant. So up to moderate pressure, the attractive forces are going to be dominant. What happens when you are having a value which is Z is greater than equal to 1? Z greater than equal to 1, what is the value we are going to get? Please plug in and tell me what will be the values.
For Z greater than 1.
Mm.
Ma'am, so fugacity will be greater than the pressure of the gas.
Yes, fugacity will be greater than the pressure of the gas.
Yes, ma'am.
And at that time, what will happen? That if the fugacity is greater than the gas, then what will happen? Then the chemical potential of the real gas will become more than the ideal.
Yes, ma'am.
Okay. So when will the values of chemical potential of real gas be greater than that? Can that be greater? Yes, it can be greater. It will be greater only at very high temperatures, high pressures. And at this high pressure, what happens? the fugacity becomes greater than the pressure which is of the gas, and repulsive forces are going to be dominant in this region of the pressure. So at very high pressure, the Z plus Z is greater than 1 is going to be dominant, and that time we can have a chemical potential of the gas which is real is greater than the chemical potential of the ideal gas, which you should get from the PV equal to nRT equation. Am I clear?
Yes, ma'am.
Okay, I think I'll end today's lecture with this ideality, non-ideality, and take up simple mixtures. So we have taken simple mixtures already in pure state, one component system. Now I'm going to take up two component system in the next class. Okay. Now tell me if you have any questions till now. And please derive this on your own. If you are taking down a little bit also, please derive the expression for the phi from the compressibility factor. Suppose I give you an equation of state. Okay, Z, you can find out what is going to be Z. Z is the ratio of the molar volume of the real by the molar volume of the ideal. So if I suppose give you, I think I have given you this question in your assignment sheet. If I don't use PV equal to nRT, if I have a van der Waals equation, or if I have a virial equation, then how will this expression look like? You should be able to evaluate.
Yes, ma'am. There is one question in the assignment.
Yes, there is a question in the assignment where if you are Z has to be evaluated for a gas which is not real gas. I mean, it's not the real gas equation PV equal to nRT, but I've given you the equation of state for that particular condition. You apply that and find out Z and put in the Z here, and then you can easily find out what will be the value of phi. Right? So what things which we have learned in this, that we have a term known as associated with non-ideal gas, that is real gas, a term which is a pressure term, which can be replaced in the equation of G instead of pressure when we are talking about a real gas. The equations for the G remain same. Only modifications we have put in is in pressure we have written down fugacity. If I write down that in terms of fugacity, what I have tried to find out, what will be the difference in the molar volume of the real gas and the ideal gas, real gas minus the ideal gas, what will be the difference in molar volume if I have a system which is ideal and real, and I want to find out the difference between them. Okay, and from that, from finding out that difference, I get to manipulate conditions so that I can get an expression where I have something in terms of the compressibility factor minus 1 divided by P into ln P integrated over 0 to pressure 0, initial pressure of 0 to pressure P in the final. All these being considered is under constant temperature. Okay. So if you look at this graph, when we are having pressure which is higher, then the deviation from pressure to this will be otherwise pressure, or fugacity will be equal to pressure when we are having come to the standard state, but the deviations start setting in at higher pressure.